Hello and welcome back. We are finishing off this unit with, oh, that was weird. To make sure you're actually able to see my screen there. Apologies. There we go. We are finishing off this unit by looking at some more arbitrary functions. When it comes to doing these proofs. So here we're gonna, rather than be given actual values for f and for g, we're just saying let's prove that if f of theta, f is in theta of g, then g must be in theta of f. And we're gonna prove it at that very, very high level, using the properties that we have. So let's start off by reminding ourselves what this actually means. We're proving that f is in big O of G and f is in big omega of G. And, or I guess we should say then, G is in big omega or big O of f, and G is in big omega of f. So those are the two things here that we're gonna be saying. So let's start by assuming one side is true, and let's see if we can work our way to the other side. So let's just move this out of the way for a second. Oops, move this out of the way for a second, and let's go and take a look at our properties. Now, again, when we're dealing with theta, there's only so many that we can work with. Let's go ahead and grab this one. And since I know what I'm going to need, and I can see it's right below it, the fact that if f is in big O of G, then G is in big omega of f. And we've seen this one already before. We've drawn some graphs. Go back and look at some of the other videos if you need a graph reminder of what that actually means, because we're going to use the fact that we understand what that is now in order to solve this problem. So by 3.1, we know this statement right here, right? That's actually what that means. That's what that statement actually gives us. And by 3.2, we know that that if this is true, this is true, if and only if this is true, right? So, pardon me. So if we are indeed going to believe that f is in big O of G, then G must be in theta, or sorry, omega of f. And similarly, I can spell, it follows that if f is indeed in big omega of G, then G must be in big O of f, right? So using that same proof. And then once again, we can look at using 3.1 again, we see that G is in theta of f and G is in O of f. Therefore, G is in theta of f. I think I said theta before and I meant omega. So let's color code this a little bit because I think it's going to help. So we took our original statement of f being in theta by looking here and here, by saying that's actually what that means, right? It means that f is in big O of G and f is in theta of G. Now, if f truly is in big O of G, then by 3.2, we can see that G is in theta of f. And using that exact same logic, if f is going to be in theta of G, then G is going to be in big O of f. So we're just reversing those. And what we've now done is we've established how both of these two terms can come to be while these two terms are true. And so using those two terms, we can then say, since we know that that's the case and that's the case, using 3.1 once more, we're going to end up working backwards to f being in theta of G, so G being in theta of f. and we were able to prove it. Now, it's not particularly difficult. It really is just basic logic. We're able to prove it at any abstract level, that this is a true statement. Now, this isn't a particularly long exercise, so I think what I'll do is I'll continue and I'll go to the next one as well. Oh, where is the next one? I never pulled it in. Okay, let's go grab it and let's walk through it. I thought I had grabbed it. Hold on. Here it is. Okay, let's grab that and go back over here. Paste. Sorry for that. Okay, so we're looking at this exercise here. For any constant c greater than 0, we're going to prove that if f is in omega of 1, then f plus c is going to be in theta of f. This is probably, if it's not blatantly obvious, one of the most complicated ones that we will have seen up until this point. There's a lot of different pieces here. Let's try not to get too bogged down, because it's really not too bad once you sort of take a breath and break it out into pieces. So let's just start at the very top of this. Let's remind ourselves that we're going to let c be any kind of constant, right? We don't know, it's a constant. And we can suppose that f is going to be in big omega of 1, right? So if we're going to assume that that's true, then we're going to prove, we need to prove our claim that f plus c will be in theta of f. And now, as we know, showing theta of f, we have to use one of our properties. Now, we're going to use the property that we used previously. I'm just not going to re-pull it down. It's right here by 3.1. We can say by 3.1, we need to show that, we'll do it in 2 lines here. F plus c is going to be in omega of f, and we need to show that f plus c is going to be in big O of f in order to prove that original statement. So in order to prove, this statement right up here, we need to prove this is true, and we need to prove this is true. And again, if you draw the graph, it might help you sort of visualize it a little bit better, and we're going to see exactly why this is true. Okay, so let's go back to our list of properties and grab the other property that we can use with respect to the theta, which is right here, right in our multiplication. For any constant c greater than 0, c times f will be in theta of f. And that's, of course, going to be a really big one while we're trying to prove something being in theta of f. So let's go ahead and grab that right there. Okay, so using this right here, by 5.1, it follows that f alone would indeed be in theta of f, right? That makes sense. And so then it follows that with 3.1, we can say that f will be in big omega of f. And using what we've seen previously as well, using 4.2, which a reminder is if f is in big omega of h, then f plus g is in big omega of h, something like that. If f is in big omega of f, probably supposed to be f. I can't remember. I don't have them memorized. You don't have to memorize them either. Let's go look and see, because I can't remember. Oh, it was h. Curses. I second guessed myself, but it was h. Okay. We can put h back so that it matches the property properly. Right? We can add anything we want onto that function, and we're not going to mess up the lower bound for our function. That lower bound does not move. So therefore, it follows that f plus c will be in theta of F. So what we've done is we've taken this statement here. We used 5.1 to show this, to get this. We knew that that was true. After doing that, we were able to break up the fact that F is in theta meant that F had to be in big omega of F. And then we could use 4.2 to say, no problem, add that C on and we'll still be in big omega of F. So now we've shown that entire side. We now need to look at the other side, right? That F plus C is going to be in big O of F. So as we previously noted, right, where did we say it? Right up here. By 5.1, we also know that F is in big O of F, right? So here we said that we knew it was going to be in big omega, but we also know it's going to be in big O of F. So then using the same rule that we did up here, that 3.1 rule, therefore by 3.1, it follows, I guess we can do that F is in big O of F, right? So we used 5.1 to see that we were in theta, and then we used our definition of theta to show that meant that F would also be in big O of F. Okay, then we can show from, let's see here, then by supposition, so we can just, this is just like fact, right? By, I don't even want to use supposition, that's in the notes. By big facts, by big facts, F is going to be in omega of 1, because a reminder, last time, what does that actually mean? Here's our graph, big omega of 1, that's right here. So we're saying constant time. We're saying that technically the best we could possibly do for F would be constant time, which is true. You can't get better than constant time. Absolutely everything in our graph is going to be above big omega of 1. So we're just saying that that's just a true statement. It's just a big fact that we know that that's true. So then, oops, I'm in the wrong color. So then by 3.2, we find that F is going to be in, oops, by 3.2, we're going to find that 1 is going to be in big O of F. And again, we'll draw the graph for this way as well. What we're saying is if this is F, this is big O of F, 1 has to be somewhere in here, 1's all the way at the bottom. So that's also sort of just like a true fact. We do actually reference a property for that, but I mean, I guess all of these are true facts, but sometimes drawing it out really does just sort of help us see what's going on. So we're able to then say that 1 is in big O of F. So then what we can do is we can go back to 5.1 and look at, by 5.1, this implies C is also going to be in theta of 1, which we know to be true. This is something we've said multiple times actually throughout the course. We've said that anytime you have a constant number of operations, it's constant. We just call it big O of 1. It means it doesn't rely on n. It means it has nothing to do with the input size. So 5.1 does imply that C is an element of theta of 1, which when we break that up, which by 3.1 means that C is an element of big O of 1, and C is going to be an element in big omega of 1. Now, where did we see big omega of 1? We saw it right up here. Let's not forget that. And there was a reason why we wanted to get that. Because now we can actually combine these facts here. And we can say that using 2.1 and our big fact and big fact, right? By combining those two pieces of information, we're able to actually say that C will end up being in O of F. If you don't remember what 2.1 is, that's going to make this trickier, but it's another one of those transitivity rules right here where we're saying if F is in big O of G and G is in big O of H and F is in big O of H, right? This is like my favorite. I should have it on a t-shirt. So what are we saying? We're saying by that rule and the fact that right here we say F, or sorry, 1 is in big O of F, and where is it? And C, so C is in big O of 1 is in big O of F, therefore C is in big O of F. So once we've managed to prove that C is in big O of F, we can then combine, let me do some highlighting here. So we've now managed to show this, and we've shown this by this step here and this step here. And now what we can do is we can actually go back and grab the fact that we proved this right here, right? That because F was in theta of F, F was in big O of F. And then we can also take the fact that we proved this right here, which is that C was going to be in big O of F as well. And these are both in big O of F, as we can tell. When we smush these together using 4.1, we know if F is in O of F and C is in O of F, then F plus C will be in O of F, right? We get to combine those. That's what 4.1 tells us we can do. That's that addition rule that we've seen before. And so now we have actually come full circle. We have proven that when we have any constant C and we started with F being in omega of 1, I think I called it big facts, but that's fine. That was our assumption that we did at the beginning, right? We were able to prove that F plus C would also be then in theta of F. When you try to read it all as one sentence, I will say I find it can be really confusing to understand what's happening. But when you break it down and walk through it step by step, sometimes that's a little bit easier. So spend some time with these problems. Spend some time being able to explain these problems to your brother, your sister, your partner, your rubber duck, whatever it might be. Because being able to explain it in plain English, to be able to draw like the graph is going to help you immensely when it comes to solving these problems on your assignment and potentially an upcoming midterm. Okay, and with that, I will close off this intense unit of asymptotic notation, and we will be using what we have learned as we go through many different Java-based data structures in general and their Java implementations, and we will see how these data structures stack up to each other with respect to their asymptotic notation. Okay, thank you everybody, and have a great rest of your day.